continue back on the introduction chapter part 5. So for this one, this is the last part of introduction. This is focusing on system type, static error constant, and steady state errors. System type is defined to be the value of n in the denominator, or equivalently the number of pure integration in forward path. So the value of n in the denominator, in this case, this is n. Okay, if this is contain s squared, n equal to 2, so this is type 2. This is s with a power of 1, so n equal to 1, this is type 1. And this is actually s with a power of 0, which is equal to 1. So we didn't write it here. So n equal to 0, this is type 0. So it's very easy to determine the system type based on the value of n, okay, of the denominator of a system. So steady state error is the difference between the input and the output, as described in the second order system underdamped response in previous figures, part 4, for a prescribed test input. So this is the test input. Test input used for steady state error analysis and design are summarized in this table. So we have step, ramp, and parabola input. Step input represent a constant position, okay, constant position, and thus are useful in determining the ability of the control system to position itself with respect to a stationary target. The Laplace transform is 1 over s. Ramp input represents constant velocity inputs to a position control system by their linearly increasing amplitude. And the third one is parabola, whose second derivatives are constant, represent constant acceleration inputs to position control system and can be used to represent accelerating targets. Constant velocity inputs to position control system by their linearly increasing amplitude. Okay, and for parabola input is 1 over s cubed, for ramp 1 over s squared, for step 1 over s. This is the static error constant formula. Position constant Kp, limitation s equal to 0, Gs. The Kp will have a constant value for type 0. The next one is velocity constant, we label as Kv, where the formula is limitation Sgs, where s is approaching 0. So Kv will have constant value for type 1. And the third one is acceleration constant with label Ka, and the formula is limitation s squared Gs, where s is approaching 0. Acceleration constant Ka will have constant value for type 2. So this is for type 1, this is for type 0, type 1, and type 2, which will have constant value for each static error constant. Otherwise, it will be 0 or infinity, as described in this figure. So for type 0, Kp will have constant value, Kv and Ka 0. For type 1, Kv will have constant value, Kp infinity and Ka 0. For type 2, Ka will have constant value, while Kp and Kv will have infinity value. This is to determine the error. The error formula is for type 1 is 1 over 1 plus Kp. Kp is the static error constant for position constant. For type 1, this is how to determine the error, which is 1 over Kv. The rest is 0 and infinity, while for this type 0, for ramp and parabolic input, the error is infinity. And this is to determine error for type 2, 1 over Ka, the acceleration constant, while for error for step and ramp input, the error is 0. You can try to determine the system type, static error constant, and find the expected error for this step input. When you know the step input, of course, this is type 0. How to confirm it? Here, this is actually S with a power of 0. So N is equal to 0. So this is type 0. And then you determine the static error constant Kp, which is equal to limitation GS, where S is approaching 0. So this S is become 0, S0, S0, 0, and 0. So Kp is equal to 500 multiplied with 2 multiplied with 5 divided by 8 multiplied with 10 multiplied with 12. So you will have the value of constant Kp. And to determine the steady state error for type 0 is equal to 1 over 1 plus Kp. So you can try this example for step ramp and parabolic input. So for this one, you know that this is type 0. Okay, S to the power of 0. Okay, that's it for part 3. That's it for the last part 5 for introduction. Thank you very much.